Hello, I'm Brooke, and today I will be going over the 2015 AP Calculus BC FRQ number 6, which is a Maclaurin series. The question gives a function f by this series, and it converges to f of x for the absolute value of x is less than r, where r is the radius of convergence of the Maclaurin series. Part A asks to use the ratio test to find r. Part B asks to write the first four non-zero terms of the Maclaurin series for f prime, the derivative of f, and express f prime as a rational function for the absolute value of x is less than r. And Part C asks to write the first four non-zero terms of the Maclaurin series for e to the x, and use the Maclaurin series for e to the x to write the third degree Taylor polynomial for g of x equals e to the x times f of x about x equals 0. Let's begin with part A. So in part A, we need to use the ratio test. The ratio test is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, where a sub n is the series given, and a sub n plus 1 is the series with n substituted for n plus 1. So in this case, in the case of this series, we will take the limit as n approaches infinity of the absolute value of 3 to the nth times x to the n plus 1 over n plus 1 times the reciprocal, because we're dividing by the original series, which is n over 3n minus 1 times x to the nth. For the negative sign in the negative 3, we can disregard that because taking the absolute value of any negative number will always result in a positive number, so therefore the negative number will play no role. We can see that the 3 to the nths cancel, and the x to the nths cancel as well. Now there's still going to be a 3 to the negative first in the denominator here, and an x to the first in the numerator here. Simplifying, we get the limit as n approaches infinity of the absolute value of n over n plus 1 times 3x. When we take the limit as n approaches infinity of n over n plus 1, we get 1. So we're just taking the limit as n approaches infinity of 3x, which gets us 3 absolute value of x. The 3 does not have to be in the absolute value bonds because the absolute value of 3 will always be 3. When we use the ratio test, the answer we get for the ratio from the ratio test, in this case 3x, has to be less than 1 in order for the series to converge. So we set that 3x to be less than 1, and we divide by 3 on both sides, which gives us the absolute value of x being less than 1/3, and that's in the form here, where the absolute value of x is less than r. So we know that r will be 1/3. Next is part B. In part B, we are to write the first four non-zero terms of the Maclaurin series for the derivative of f, and express f prime as a rational function for the absolute value of x being less than r. So I'm going to split this into two parts. The first part will be to write the first four non-zero terms. As we can see here, the first three non-zero terms are already given to us, and we can find the fourth term by simply plugging in 4 into this series expansion right here. So we get negative 3 to the 4 minus 1 over 4 times x to the fourth, which simplifies to negative 27 over 4, x to the fourth. And we already have these first three from here. Now we just take the derivative by using the power rule, and we should get that f prime is 1 minus 3x plus 9x squared minus 27x cubed. In the second part of part B, we have to express the derivative of f as a rational function. Okay, so in order to take the derivative, we simply use the power rule on the series. Since it is x to the nth here, we simply multiply the n in front and subtract 1 from the power, and the n's here cancel, so we get negative 3 to the n minus 1 times x to the n minus 1, which simplifies to negative 3x to the nth minus 1 from n to infinity. We can also rewrite this as negative 3x to the nth from 0 to infinity. No matter which way you write the series, the derivative of the original f, they will both be geometric series. And in order to find the sum of the geometric series, we take the first term and we divide it by 1 minus the common ratio. In both cases here, whether we plug in 1 into this series or 0 into this series, we will always get 1. And we can see that the common ratio in both of these is negative 3x. And simplify, so we get 1 over 1 minus negative 3x, which gives us 1 over 1 plus 3 to the x. Next is part C. In part C, we are to write the first 4 non-zero terms of the Maclaurin series for e to the x. Then use e to the x to write the third degree Taylor polynomial for g of x equaling f of x e to the x. So I highly recommend for the AP test to memorize these non-zero terms and series for e to the x, sine of x, and cosine of x, because one of these problems will likely appear on the AP test asking you to write the first 4 non-zero terms or the series in general, and it's easy points if you just have them memorized. So e to the x, the first 4 non-zero terms, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And we know that for f of x, to the third degree, it has been given to us, and it is x minus 3 halves x squared plus 3x cubed. Now we only need to write up to the third degree because we're using it to write the third degree Taylor polynomial. And so we only need to go up to the third degree in order for us to find the third degree Taylor polynomial. So in order to get g of x, we multiply e to the x and f of x. And we just simplify the factorials and multiply across, and we get this. Notice that when I multiply, for instance, x by 3x cubed, I get 3x to the fourth. But since we're only finding the third degree Taylor polynomial, we don't need to write it because 3x to the fourth is a fourth degree polynomial, and that will not be included in our final answer. Simplifying all of the correct numbers, which are listed here, we get that g of x is x minus 1/2 x squared plus 2x cubed. If you would like more practice with the type of problems covered in this video, I recommend you do either the 2014, 2009, or 2002 AP Calculus BC FRQ number 6s. The questions in these problems have similarities to the ones we covered today and will give you more practice. Thank you for watching, and I hope this video helped you.